Oh, right.
That's fine. Okay. All right. So it's week 6. We're doing workshop number 4 on signal processing. Actually, we're not going to really introduce the BCIs. That's going to be more so week 9. And yeah, once again, if you just got here, please kind of scoot forward so that we don't have to yell as much. That kind of really strains the voice. So I guess, yeah, once again, week 6. Last week we did intermediate Python. This week we're going to continue doing stuff with Python, but specifically, we're going to be just kind of decomposing signals, kind of going more into the theory of signal processing. And we'll also have another Colab notebook. So right now it's just a theory, so let's start with that. First of all, with signal processing, there are a lot of courses out there, or specifically these two, I guess. There's, electrical engineering, signal processing, and digital signal processing as well. And so, first question, of course, what are signals? Can anyone give, a brief explanation? It doesn't have to be correct. It can be a kind of a guess even. Feel free to discuss also with your partners. Oh yeah.
Like a time series of DC value and amplitudes that you read in to extract information.
Yeah, wonderful, Adrian. So
just quickly, what's one example of that? Like something that you interact with on a daily basis? Like just what's one signal that you interact with every day? Any type of signal. Great. Yeah, radio wave, sound wave, light wave. Those are all different types of signals, and exactly what you said. They can be visualized in a lot of different ways.
Yeah, so this diagram kind of just shows that, but just anything that has like a kind of variance with respect to time. That is an example of a signal. Yeah, and examples that Davis gave, that's like sounds that could be like Wi-Fi signals that's propagating through EM waves, X-rays also that, sonar that's like ultrasound basically, or just like kind of really high frequency sound. And so someone put a quote here: if you have ups and downs, then life has something to tell you. And if you look on Wikipedia, a signal is just any time varying quantity. And when I first was looking at this, I thought signals were specifically about like the transfer of information, which is how it's colloquially used. But actually, signals also include noise. We actually try to separate information from the noise because noise, nobody likes noise, I suppose. And what we don't know is what is the noise in the signal and what is the information. And so here, this little diagram kind of shows like a signal, like an overall signal. Sorry, it shows a sinusoidal signal, which could be like interpreted as the information. And then we have white Gaussian noise and then some impact noise. And so when you add them all together, it's kind of messy. And what we would like is to be able to decompose this messy signal into just kind of the sinusoidal signal, or like this kind of information, and then also the white noise. And so, yeah, we can define this white Gaussian noise later. Essentially, it's just kind of like random noise that you might have seen last week. It was this random Gaussian noise that we added to signals, but we'll go more to that later. And yeah, noise is usually just any high kind of frequency stuff. So you'll see here with the white Gaussian, it's just like very like a seismic needle or something. Yeah, and then so how do we know what is high frequency or what is noise? Can anyone kind of give like a good, doesn't have to be good once again, but can anyone give like a reasonable answer? Yeah.
And there's like a region like where like that sign vector is really compressed at like via first kind of like we usually call it
Yeah, I didn't quite catch the last part, but everything sounded correct. So, okay, so waves. I guess this doesn't really answer the question, but high frequency waves just means you have a lot of compression, or you have kind of a lot of like the yeah, you can read the memes. You can, it's like a lot of a sample happening in a short amount of time, basically. So that would correspond to like a compression. And so, yeah, waves, they interfere all the time. Interference just means that you add up their amplitudes with respect to time. And so you can have constructive interference, meaning you have kind of with like, if you have, for example, this green and kind of red and blue, they're all adding up into like a positive direction. So if all the waves are adding up in the same direction, or if their amplitudes are in the same kind of sign, then you have constructive interference. And yeah, this is basic kind of physics stuff, but you also have destructive interference with if they have opposite signs and they add up to kind of cancel each other out. Yeah. So what we see is not just one wave, but a mix of waves. So who can kind of like say which one is kind of the overall wave, which is like the kind of resultant wave of adding up the other ones? Yeah, black. You can kind of see with green, it's like you see black is following green, but it's also following red and also blue. So yeah, if it was a more complex signal, there's actually computer algorithms to do this, and yeah, not just computer algorithms, but there's also like mathematical tools you can use. And so this guy, this baby face over here, his name is Jean, I don't know, Fourier, and thanks to him, he kind of discovered like the Fourier transform, which allows you to decompose a wave going from amplitude versus time in that kind of axis. Like for example, this is amplitude versus time, and you're able to convert it into amplitude versus frequency, which is a lot more useful when you're trying to like filter out noise. And so here's kind of like a brief, short infographic of this Fourier transform. You can kind of ignore the math for now, but here you have like in, for example, an EEG brainwave, and it's very messy, and you don't know what are all kind of the like smaller frequencies or what sinusoidal waves it's made out of. And with this Fourier transform tool, just ignore the math once again, but just imagine that you're able to use this tool to convert it into this kind of graph right here. This is called frequency domain. So we're able to convert it from time domain, amplitude versus time, to amplitude versus frequency. And we're able to see that this kind of brainwave is made of, this alpha wave, this beta wave, gamma wave, and so on. So it's made of waves at this frequency, at this frequency, and at this frequency. Okay, so that's what the Fourier transform is. And this is the actual math. This is how you get kind of the transformation. So this f of x would be sort of the brainwave right here, and this f hat of k, where k is kind of like the frequency. That is going to be kind of this graph right here. And yeah, honestly, you don't really have to know the theory behind this that too much. It's going to be like totally abstracted away when you're like coding. It's just going to be like some simple function, and you're able to plug it in. So you plug in this thing, and you get out this thing. But yeah, more onto the mathematics really briefly. Yeah, honestly, you can ignore this. There's actually a kind of a cool video, but I think we'll probably skip it for now. But yeah, there's this really cool like math YouTuber. His name's like 3 Blue 1 Brown. But if you're interested, you can watch that video, or you can ask us during break. Just how the math works behind this kind of Fourier transform. And so yeah, when you convert from this amplitude time versus time domain to like the frequency domain, once again, you're able to kind of see where the high frequency noises are, and you're able to just like do a filter on it. We will do like I forget if it's a low pass or high pass filter. Yeah, just a bandpass filter. You can kind of like just remove this noise so that it's only these sounds that you care about. Yes. And then, yeah, when we filter signals, sometimes we get, predictable interference from our environment. So can anyone give an example of, noise that might appear in our environments, at least when we're trying to measure like EEG signals? Yeah, I saw you had your. But I saw you had your hand up briefly. It doesn't have to be relevant to BCIs or EEGs. Yeah, go ahead. Yeah, that works. That is some form of noise. And just think when we're measuring like EEG waves, we're trying to measure electrical activity. But there's also a lot of electrical activity around us, like just randomly. So can anyone kind of give maybe perhaps a source of where this electrical like EM waves are coming from? Yeah. Yeah, that's a good example. But there's actually something else that actually produces a lot more noise, and light, that's
Also,
not exact.
yeah, you don't really see that as much in like the domains that we're looking in for EEG specifically. When we're actually looking at EEG signals with one of our caps, and we're in a room, we'll often see one very predictable source of noise, which are AC currents, which are in any room that has electricity. You can.
Yeah, so kind of in the US, there's going to be alternating currents. At least that's how they power like the outlets basically. And it's going to be 50 hertz for everywhere outside the US, and inside the US is going to be about 60 hertz. And so if you pull up kind of the FFT or the Fourier transform of your brainwave signal, you're going to see a massive spike kind of around the 60 hertz frequency range. And so we have to apply a filter on that just whenever we're doing this stuff. And so I guess there was someone gave the example of cell phones. I think the frequency on cell phones is just way too high. It's like, I don't know, like gigahertz or something. So you won't see that with brainwaves. Brainwaves are about like, less than 100 hertz. So only 100 or so like electrical signals kind of happening per second.
But if you are charging your cell phone next to an open BCI cap while you're trying to record EEG signals, you will 100% see the 60 hertz frequency as noise in your signal. For that matter, you don't have to be charging your cell phone. Any room that has outlets in it, you're going to see that frequency. And it's so common that you'll see this next quarter once you actually start working on BCI teams. It's so common that OpenBCI builds a 60 hertz bandpass filter into their graphic user interface so that you can just automatically filter that out. They also have a 50 hertz one for people working outside the US.
Yeah.
But it's very common.
Yeah. And so, yeah, this is already answering you, right?
Yeah.
Okay. So, yeah, we kind of just answered this question, but we can apply bandpass filters to selectively observe certain frequency ranges. So here we just do like we like decompose the signal into its theta wave, into its alpha wave, beta wave, gamma waves, and we just see like the kind of amplitude in terms of, I guess, voltage versus time. Yeah, so now we'll go into the Python Colab notebook, but really quickly, we didn't actually get through the entirety of last week's notebook. There was actually some unanswered questions, so I'll very briefly go through that. So there was this kind of question right here, which was like, plot the following in subplots. So this is back to the intermediate Python workshop. And I just want to show you that if you don't know the answer, it's actually really easy to kind of find it online, not just through Stack Overflow, but through like AI. So in my research lab, my professor he's constantly kind of dissing us students. He's saying like, whenever I use ChatGPT or whatever to write the code, it does it like 100 times faster, and it also does it 100 times better. So I'm gonna show you how to like use this really quickly. So you can just like copy this and go to like OpenAI, ChatGPT. You can, plug in the prompts, and you can ask to plot the following in subplots in matplotlib in Python, or you can say using Python, and it can generate this code for you. And we'll run it later, but you see, it's just like very quick. Obviously you can ask, like, okay, first of all, it comments like what it's doing. And you can also ask like what individual part means. So it's a pretty good learning tool. And so if we actually like plug this in. Yeah. Yeah, it will basically just give you the answer. So yeah, just if in the future when you're coding, AI tools are very going to be the future basically. Yeah. And so now on to our actual signal processing workshop. Yeah, I'll go up until the screen. Yeah. So for a analysis. So I guess this, okay, just to preface this, we have oh yeah, also do you guys have access to this notebook, this workshop 4 notebook? Yeah, I see thumbs up. Does anybody not have access to this notebook? Okay.
Raise your hand really high if you need help getting the notebook on your computer.
Okay. Yeah, okay, I'll just get started anyway. So last week we also covered this lint space, but we'll cover this really briefly again. So this is just a way to generate an array of points basically, or array of numbers. And it gives you can kind of just plug in when you want to start the list of numbers, when you want to stop, the number of numbers, and also some other settings that we won't really go into. And so here, this is like a demonstration of wave superposition or wave kind of interference. And so when I run this, you see that we have, I guess, plots for x1, which is just sine, x2, which is that, x3, which is 3 cosine of 4t, and then we also plot in the end x1 plus x2 plus x3, just to demonstrate like wave superposition. And so the goal when we're looking at these kind of graphs is just to like decompose this addition thing back into x1, x2, x3. And so yeah, moving on, we're also going to demonstrate that it's possible to kind of create any sort of periodic function using kind of a linear combination of a bunch of sines and cosines. So this is kind of like what we call like a Fourier series. And so yeah, we'll make this. And so here we get like an approximation, which is initially just zeros. And then we add only sines, really. Here we're only adding sines. We're not adding like lines or anything. It's just only sines. But we've kind of vary the frequency of the sines and also the amplitudes such that when you add them all together, it produces like a square wave. So that's kind of a neat trick. Yeah, honestly, this is not going to be used too much in like signal processing, but it is related to the Fourier transform. It's actually kind of like the inverse of that in a way. And now we'll get into the discrete Fourier transform. Can I just keep using it? Bricks. No, I think break. Yeah, maybe.
You guys want to take like a 5-minute break before we continue? Raise of hands if you want a 5-minute break. Okay, keep going. the link is not working for the notebook? Who's talking right now? Oh, will you help him? Is anyone else having that issue? This, okay. Yeah, you might need to install Colab. Okay, how about we take 2 minutes to just talk to your neighbors and ask them their names and their majors and anything else that you want to know about them and get to know each other. Just thought it was like get people talking.
Yeah, so they're gonna fall asleep.
Yeah, otherwise they fall asleep. We honestly don't even have that much left.
Yeah.
So it'll be pretty quickly.
Yeah.
I think it was much better because
I think this workshop is just a lot shorter. Anyway.
it is shorter, yeah.
Yeah.
And I think like having the more like asking more questions, like having people actually get involved is a lot better.
All right.
So we'll make more adjustments for next week. Yeah.
I think we need more Confederates, you know.
Yeah.
People like asking questions.
Yeah. I mean, but it's good. Like honestly, people are like more engaged than I expected that they would be. It's quieting down. It's been like 2 minutes, right?
Yeah. Can you also ask again?
What?
Can you ask again for people to mute that?
Yeah.
All
Disruptive.
right.
Okay. Okay, everyone. Okay. Were you able to get it working? Okay, cool. All right. So everyone has access to the notebook. Yes. Great. Okay. So welcome back. Discrete Fourier transform. That's basically what we've been talking about. There's broadly like 2 types of Fourier transforms that we do with like marginally different properties. Those are discrete Fourier transform and fast Fourier transform. Right now we're just going to talk about DFTs. So as Ethan said, Fourier transforms are a way of extracting frequency information from essentially a time series signal, which is really useful for applications like EEG. So here we have a bunch of code. I know you guys all have this open, but just looking at this signal, can anyone tell me what you would expect it to look like as a Fourier transform? Doesn't matter if you're right or wrong. Just what will this signal look like once we transform it? Yeah. Yeah. Great. It'll actually be a double spike, but close enough. So a few points of interest. The Fourier transform here is symmetric about the y-axis. We're really only interested in like the positive half of the graph, because it will always be symmetric in our application, or at least in this application. So we usually only look from 0 to infinity. I guess that's pretty much all you need to know here. Oh yeah, and then the spikes are at 1 and -1 hertz respectively. And that has to do with, as you can see, here, it's related to the amplitude, which is a voltage ranging from -1 to 1. What? Oh, yeah, the syntax. Yeah. Okay, so basically what this block of code here is doing is first we have this signal. First we have our frequency, which is 100 hertz. Then we have our time series, which is essentially 10 seconds divided, multiplied, and then you multiply 10 seconds by 100 hertz, and that's the number of time points that we'll have in our graph. And then we have our signal, which is this sine function. And then all we're doing, super easy to find the Fourier transform. Again, as Ethan said earlier, you really only need to plug stuff into pre-established functions. So the NumPy library that you should all be familiar with already, if you've been attending workshops, has this fast Fourier transform function built into it, or rather discrete Fourier transform built into it. And all you have to do is type numpy.fft.fft and put in your signal, and then it will give you the discrete Fourier transform of that signal. You also want to get the frequency components from that signal, which we're doing right here, which is numpy FFT frequency. And into that, you provide the size of your signal, the length of your signal, and 1 over the frequency. And if you plot that, this is the plot that results. Yeah, so that's basically all we're doing here. And feel free to refer back to this, like, as we go forward. Yeah. Does anyone have questions? Cool. All right, so here's a more complex example. Obviously, our signal here is a lot more complex. It has multiple components, multiple sine components in it. This is what our original signal looks like. And this is what our discrete Fourier transform signal looks like. Does anyone observe anything about this Fourier transform that was different than the previous one? Yeah. Yeah, that's a good guess. So it actually would be symmetrical. We're just only looking at the positive frequencies. So that's a good guess. But if we looked from like -50 to 50, then we would observe a symmetrical signal. But that's a really good guess. Yeah. Sure. Yeah. Exactly. Yeah. So what we can see here is there are 4 distinct peaks in this signal at 4 different frequencies. And each of those peaks has a different intensity associated with it. Excuse me. So looking at this, what you can see is here in our signal, we have 4 different sine components. And each one of these is associated with one of these peaks. So essentially what our Fourier transform is doing is it's isolating each of those frequency components and assigning an intensity to it. And as you can see, the constant term coefficients in front of each of these signals are different. And so that should correspond roughly to the intensity of that frequency component. Yeah, and the spikes are at 1 hertz, 3.5 hertz, 17 hertz, and 38.5 hertz. And yeah, the height of the spikes is related to the weight that each sine function or sine component has in that signal. Yeah. Okay. Where are we? Oh yeah, and then we can also see the corresponding magnitudes of each of these frequencies. So yeah, basically you can see that the magnitudes associated with each of these sine functions are directly related to the size of these spikes. Okay, and just to show you the Fourier transform of a square wave, as we saw before, which is basically an infinite number, basically an infinite number of sine components. It's a series of sine components to form a wave, and as that series goes to infinity, you get the sine wave. This is what the discrete Fourier transform of the sine wave looks like. So again, you see different intensities at different frequency components. If you ever encountered square waves before, yeah, otherwise it doesn't really matter. So obviously the reason that we're learning all this is to apply it to signal processing. We primarily work with EEG signals, as you know. Those tend to be extremely noisy. So for the sake of providing you with a real world example, we're gonna apply some Fourier transforms to musical chords or musical notes. Sound is a real world signal. It's a wave that we interact with on a daily basis. And so we can actually visualize what different musical notes look like using Fourier transform. So this requires a bit of setup. If you click this file link, it'll take you to this file. Is everyone able to access that? Thumbs up if you can. Okay, great. So, okay, I think what would be best is if you copy this this whole folder into your Google Drive. You might need to help them with this. So if you go, oh, I guess I can't do it because I'm the owner. But if you add a shortcut to your drive, add it somewhere that will be like really easy for you to find it. Sorry. It's okay. Actually, if you just add it into like the base folder of your drive, so just like content drive, that's the best place for it. And then you're gonna need to adjust this directory according to wherever you've placed that file. And so the way you do that is on the sidebar here, click on files. And then if you click on this Google folder thing, sorry, first mount your drive, please. And if you need help doing this, just raise your hand really high so we can come around and help you. Mark, can you help people? Can you help people? Okay, sorry. Really quickly, everyone, just pay attention to this one part. After you've added it to your drive, go to Files here, click on this, go to the Content folder here, and then inside Content, go to Drive. And then in My Drive, if you've placed it just directly into your drive, you will see the chords folder. And that's what we want you to access. So just raise your hand and we'll help you get to that step if you need help.
Wait, okay, so I'm just gonna demonstrate how to do this really quickly on my account. So I'll switch. And I'll switch to this. Okay, so let's say I don't have okay, let's say I just have this right now. So I'm gonna make a copy. You can like right click it, select all, you make a copy, and it'll copy it to your drive, or I guess it'll copy it right here. But it should be in your drive. And we move it. And then we can move that all to Colab. And we can also put it in another folder. We can call it whatever we want, chords. So I have all this copy. I have it in chords. And then, let's see. For the mounting, okay, first of all, a lot of people are missing the step. You have to actually mount to Google Drive so that Colab can have access to your Google Drive. So you click run anyway, just to get it running. And then you connect to Google Drive. You have to sign in and everything. You have to allow all this stuff, allow it to read your data. I think everyone's got it.
Yeah, I think so. For the
Okay,
most part.
I'll just okay, and then just real quickly.
Yep.
And then basically you go to Drive, you find that place where you put all the chord files. For me, it was around here. You right click that chords path, you copy the path, and you just want to put it right here. So yeah, that should work. And I guess you already have those. Okay.
Okay, everyone. Did you follow the last part of that about copying the path to the directory? That's really important. Okay. Okay. Once you can see the chords file on this right here. Wait, where was it? Okay, once you get to the chords file, what you need to do is click the 3 dots next to the chords folder, rather, and you click copy path. And what you need to do is here where it says directory, you need to highlight and delete all of this, and then paste your own path into that variable there. That's super important, or else you won't be able to access it.
Right, so someone brought up a good point. If you don't put a slash at the very end of the path name, it'll mess up. So yeah, just remember to do that.
Okay, cool.
Okay, if you still need help getting to this point, just raise your hand and we'll come around to you. Otherwise, we'll continue on with the demonstration. So what we have here are 4 chords. I have too many. Can you hear that? Okay, never mind. The volume's not working. Anyways, you can play it on your own computer if you want. There are 4 different chords. And so what we can do with each of those sound waves is we can apply a discrete Fourier transform to get the frequency components of that sound, which you can see right here. And so what this is showing is that each of these 4 distinct sound waves have a distinct frequency profile. And that's because they're essentially a composition of different sine waves. And so naturally you get a different frequency profile with different amplitudes or intensities associated with each frequency. And so essentially this is like a visualization of what our ears detect when we hear different noises. Essentially, we're just detecting these different frequency profiles and interpreting them as we interpret sound. Does anyone still need help getting to this point? Mark, can you help the people over there? Yeah. Okay, sorry guys, I know there's some like technical issues. That's a good point. Okay, everyone. Someone just made a really good point that I want to point out to everyone. You see that these different chords, they all have a different number of spikes at different frequencies. Whether or not you've been able to listen to the chords, what's one reason you think that these could have different numbers of spikes associated with them? Does anyone have a guess as to why that might be? One possible reason that might be? Yeah. Yeah, so they're all different chords. When you play different chords on a string instrument, for instance, what's something that you do? Like what distinguishes the chords? from one another. Yeah. Yeah, frequency. Like when you physically play a chord on, say, a guitar, what distinguishes one chord from a different chord? Yeah, well, the hand movement. Yeah, yes. Yeah, the notes that go into the composition of that chord. Exactly. So different chords are compositions of different individual notes and can also be played across different numbers of strings. And each string is going to have a specific frequency associated with its vibration, depending on the note that's played on the string and how many strings are played, etc. So that was just one interesting point. One thing that could determine the number of spikes that you see are the number of strings that are being plucked, or the number of individual notes that are going into the composition of that chord. So kind of cool to be able to actually visualize that as like a set of frequency spikes. Okay, the last thing that we want to show you today are spectrograms. And this is a really easy and kind of neat way to cleanly visualize frequency information. So Fourier transforms, they show us the frequency domain relative to the amplitude, but they don't tell us anything about the time domain. So that's one of their drawbacks. In the same way that a time series doesn't tell us anything really about the frequency domain, Fourier transform doesn't give us access to time information. So one way that we can overcome that is using spectrograms, and these are very conveniently built into the Matplotlib library. So it's super easy to make them. Okay, yeah. So what this is showing us is time relative to frequency. Yeah, and specifically it shows us how frequency changes over time. And so when we look at the spectrogram of this sine wave, what we see is that we have essentially like an even frequency across our time domain. So the frequency is constant. It's not changing across time, which especially in like EEG applications, that's super valuable information when we're considering someone's like neural reactivity to a stimulus that we're presenting them, right? Like the stimulus occurs at a certain point in time, and what we're like fundamentally interested in knowing is how their neural activity is reacting to that stimulus, or how they're reacting to that stimulus vis-a-vis their neural activity. Yeah. So both components are valuable, and spectrograms are a great way to visualize them at the same time. Yeah, and the two yellow lines here correspond to the frequencies that compose our signal. And brighter color bars correspond to a higher intensity. So in the same way that here, like a higher spike corresponds to a higher intensity, this is essentially just like a heat map where the more intense the color is, the higher the intensity of that frequency is. So for instance, like at a frequency of 5,000 hertz, the intensity is effectively 0, basically. Yeah, the axis is off here, but that's okay. Okay, and so again, if we look at a more complex example, here essentially what we're doing is we have two separate waves. So here, data 1, we have this sinusoidal wave composition, and data 2, we have a separate composition. And then we're effectively just concatenating them together, which means mashing them together. So we have two separate frequency waves, or two separate waves with two distinct frequency profiles connected here. And so when we plot the spectrogram of this, well, I guess what's one thing that you observe from this spectrogram? Anyone? That's different than the previous one. Exactly. The frequency is changing over time. And we can see where that change occurs, which is basically at like T max over 2, like halfway through the signal. The frequency changes. And the reason for that, well, can someone explain the reason for that based on like these 3 lines of code here? Yeah. Exactly. Yeah. Like I said before, it's 2 separate functions here that we basically just mash together. So we have like chunk 1, like 0 through 5 seconds, and then chunk 2, like 5 through 10 seconds. And so what you can see is at the 5-second mark, the frequency profile changes. Exactly. Okay. And so we can also okay, well, this was a do-it-yourself, but I guess it's already in the notebook because maybe we didn't send around the most up-to-date one. So, okay, well, anyways, that's okay. Okay, so in that chords folder, there's an unknown sound. Do you guys have this kernel in your notebooks already? Yes. Okay, that's unfortunate. Anyways, well, if you look at the unknown sounds, this is the spectrogram frequency and time profile of that unknown sound wave. So I guess what we can do is replicate this using one of the other chords. So why don't you try to make your own spectrogram based on chord 1, or really you can choose any chord. Try to plot its discrete Fourier transform as well as the spectrogram associated with it on your own. And then we'll present the solution up here. So take like 5 minutes to do that and work with your neighbors if you'd like. And we'll come around and help you as well. Oops.
We just copied it.
Yeah.
For this one. Should have gone through and double checked. I didn't realize this was an example actually. Because usually they have like a little comment.
Yeah, I know. I think I have it must be different.
It's nice to like.
I mean, we're pretty much at time anyway. I forgot to say. I mean, that's the end of it. It was pretty neat. Yeah, dead silent. Yeah, no. Yeah. I think it's also really good to be doing like the conceptual stuff. I think so too. I think having it in their slide would be definitely positive. Exactly. All right. Was anyone able to make their own Fourier transform or spectrogram that they're excited about? Or no? Okay, feel free to keep working on that or like work on it between now and next week and come back with a really cool graph and we'll give you something cool in return. Okay, that's it for our notebook. Before everyone leaves, who learned one useful piece of information today, at least? Okay, what did you learn? One thing that you learned. What? Yeah. Oh, what's your name, by the way? Nice to meet you. Yeah, that's a good thing. Okay, who else learned something useful today? Yeah. What's your name? Serene, nice to meet you. Yeah, that's super important. And like I said, next quarter, once you actually start working with our open BCI headsets, you'll be able to see that. So before you even like put it on your head, you're going to see a frequency at 60 hertz and it's going to look very much not like an EEG signal. So it's just cool to see. I think it's cool to see how like real world interference actually works in our applications. Yeah. Okay, one last thing. Someone share one last thing that they learned. Yeah. What's your name? Okay, nice to meet you.
I'm excited. Just like I feel like this kind of like spectral analysis kind of gave me like a much better idea of like what this sort of analysis is going to do in like the brain of the BCI groups. Like I can get a sense of like what we're going to be doing, like in terms of like the frequencies, time, and kind of orienting analysis.
Cool. Yeah, that's awesome. Yeah, exactly. You're actually going to be doing this on your BCI teams, which is cool. And there's a lot of other more complex